Hello everyone. Today we are moving forward from the last class, atomic structure part 3. In this lecture we will see hydrogen spectrum. The first is our hydrogen spectrum. So see, in the last class we have discussed about emission spectrum and absorption spectrum, little bit of absorption spectrum. See, hydrogen spectrum is an example of line spectrum, right? It's an example of line spectrum, or it's an example of atomic spectrum. It can be obtained by, if you pass, see, if you have hydrogen in the discharge tube and if you pass current, then a ray of light will pass. If you can pass it through a slit, after incidenting on a prism, it will divide into different band of colors, different lines of colors, actually different lines of colors, and one of them is visible. You will get ultraviolet, you will get visible, and you will get infrared rays from hydrogen spectrum. This, see, can be obtained by passing an electric discharge through the hydrogen gas. You have hydrogen gas here and you are passing electricity here, taken in the discharge tube under low pressure. It should be maintained in low pressure. Series of lines are obtained in the infrared, visible and ultraviolet region. Now this visible region, we can see it in a photographic plate. We can see it in a photographic plate, or spectrograph. We can see it in a spectrograph or photographic plate, and the rest, that is ultraviolet and infrared rays, can be seen through by some special techniques. We don't have to learn this in this section, but this visible section it can be projected in a photographic plate. There are various lines of regions. The first one is Lehman series, which falls in ultraviolet region. We cannot see it. Second one is Balmer series. It lies in visible region. We can see it. And rest of the three, Paschen, Brackett and Pfund series, lies in infrared region. This Paschen series, Brackett series, Pfund series and Lehman series can be projected or can be seen by some special technique. In 1885, Balmer found out a relation by which you can determine the wavelength of light, that is 1 by lambda. This is wave number, that is nu bar in per centimeter, is 109678 per centimeter. This is into 1 by 2 square minus 1 by n square. That is your orbit, is that is the electron. That is, see, if this is your nucleus, this is n equals to 1, this is n equals to 2, n equals to 3. These are orbitals. Now from second orbit in Balmer series, see, the starting is from second orbit. That means the object can fall from, the electron can be excited from n equals to 2 to n equals to 3, n equals to 2 to n equals to 4, n equals to 2 to n equals to 5. Or I have already discussed about this phenomena, that if the electron jumps to a higher orbit, that is the more energy states, the higher orbit, and this is the more energy states, it will absorb some frequency of light or some wavelength of light, and it will jump. It will jump by absorbing some particular wavelength of light. And we already know that if something has more energy, then it will be less stable. As a child, right? A child has a more energy, but it is less stable. So electron jumps from n equals to 2 to n equals to 3 orbit, and as we move forward, the energy levels increases, so electron will be destabilized. So for stability, it will comes forward, or it will come to its original position instantly. So when it comes forward to its original position, it will release a particular wavelength of light. It will release a particular wavelength of light, and that wavelength we see it as a color. The color we are getting, Lyman series, BOHR'S series, these are all different colors of light we are seeing. That color we can be found out, or the wavelength we can be found out from this relation. This is an extremely important relation developed by BOHR. This BOHR. Now Rydberg comes forward and developed this equation to find out any number of series or any number of any colors of wavelength of light. See, 1 by lambda is 109678. This is known as Rydberg constant. This is known as Rydberg constant. Rydberg constant. This is your Rydberg constant, and this is from 1 by n square minus 1 by n2 square. N1 is your lower energy state, N2 is your higher energy state. So N1 can be 1, 2, 3, etc. but N2 can be 2, 3, 4, etc. N1 is your lower energy state, N2 is your higher energy state. In the BOHR series, if you have observed that we have already N1s, that is lower energy state, as 2. Lower energy state, that means electron is lying in the second orbit. But N, that is the from second orbit, it will jump to a higher energy state, that is n equals to 3 to 4. That's why we have the value of n as 3, 4, 5, 6. It can jump to any energy state except this n equals to 2. But in this formula you can see that your is a generalized form of BOHR series or BOHR relation, this relation 1 by n1 square minus 1 by n2 square. See, if you apply Lyman series, let us say Lyman. For Lyman series, n1 is equals to 1. For Lyman series, n1 is equals to 1 and n2 can be 2, 3, 4, etc. For BOHR series, n1 equals to 2. That means n2 can be 3, 4, 5, etc. For Paschen series, n1 equals to 3. That means n2 can be 4, 5, 6, etc. Yes. Now bracket series is n1 equals to 4, that means n2 can be 5, 6, 7, etc. For p-fund series, n1 equals to 5, that means n2 equals to 6, 7, 8, etc. That means your lower energy states for Lyman series is 1, BOHR series is 2, Paschen series is 3, bracket series is 4, p-fund series is 5, and it can jump from their respective lower energy state to their respective higher energy state, that is from 1 to 2, 3, 4, from 2 to 3, 4, 5, from 3 to 4, 5, 6, etc. Now see, we have learned all these things about hydrogen spectrum, which is example of line spectrum or atomic spectrum, that is the radiations emitted from atoms. Now if we talk about molecular spectrum, so it is the emission released by molecules, it is the emission released by atoms, hydrogen atoms, and it's the emission, if the emission released by molecules, then it would be molecular spectrum. Now absorption spectrum, see, if you pass sunlight through a slit, because we are restricting the light, sunlight through a NaCl solution, it will absorb some wavelength of light, from some particular wavelength of light it will absorb, and if you if the light falls on a prism, then, and if you see the colors in the photographic plate, you will see that you will get two dark bands. See, this D1 and D2 we have already discussed in the previous section. In the absorption emission spectrum, we have seen that when we passed a sodium light or excited sodium light through a prism, we got that only two yellow lines, right? Only two yellow lines. Now here if you pass this sunlight through a NaCl solution, you will the only two yellow lines which we have got in the emission spectrum, in this section in the absorption spectra, only those two yellow lines will be absorbed. That's why we can see that D1 and D2 are black in color. And see, if you observe this, that wavelength remains same. In the emission spectrum, when we got that two yellow lines, the wavelength is this much, and here also see the wavelength is same. That means you in this that's why it is known as absorption spectra, because in this section in this experiment only those two particular wavelength of light is absorbed, the rest of the colors remains as same. So let us move forward our next topic, which is Bohr's model of atom. See, Bohr's model, he proposed a he proposed a model of the atom which Rutherford explains, and he explains something else. That is, it's a modified version of Rutherford's model, and it is based on quantum theory of radiation. Quantum theory of radiation. It is based on quantum theory of radiation, and it's the modified version of Rutherford. Now let us see some important postulates of Bohr's model of atom, how it came and how it's related to, or how modified the Rutherford's atomic model. The first one is our stationary states. Let us learn about something stationary states. See, all we know that atom consists of positively charged ions and electrons revolve around them. So if electron revolve around them, that electron revolve in a particular orbit and it do not lose its energy. So the thing is that in a particular orbit where the electron revolves is his or is its stationary states. The electron, where electron resists or where electron stays, is known as its stationary states. From the states, it do not lose energy. It do not lose its energy, because see, in the Rutherford model we know that he explains that energy, electrons are revolving, so energy should lose. So if energy should lose, then it will collide with the nucleus. But as Bohr's model is based on quantum theory of radiation, he explains that electron stays in a particular orbit, and that particular orbit has fixed energy, and that particular orbit is known as stationary states, and which do not lose energy, Each of the fixed circular orbits has some particular energy levels. Each of the fixed particular orbits, see, this is a orbit, this is a orbit. Each of the fixed particular orbit has energy associated with itself. See, the general formula of energy is this: minus 2 pi square z square e to the power 4 m by n square h square. For hydrogen atom, atomic number is 1. Z stands for atomic number. N is the orbit, n is the particular orbit, h is Planck constant, E is charge of electron, mass of electron, and pi is constant. So for hydrogen atom, Z is 1, the formula comes up to be minus 2 pi square e to the power 4 m, Z is 1, right? So e to the power 4 m by n square h square. If you put all the values, see, if you put pi square value, e to the power charge of an electron, mass of an electron, and Planck constant, the value, the energy of electron, please remember this formula, and this formula, the whole formula, it's very important. The energy of nth orbit, comes out to be, after putting all the constant values, minus 13.6, we can see it as 6 because 5, 9. So minus 13.6 by n square in electron volt per atom. And if you convert it to joule, because we know 1 electron volt is 1.6 into 10 to the power minus 19 joule, if you convert it to joule, the energy comes up to be minus 1312 by n square kilojoule per mole. After that, he explains that only those orbits are permitted for which the angular momentum is your MBR, is of angular momentum of electron. Of an electron is a whole number and it's a multiple of angular momentum is constant. and its multiple of h by 2 pi. See, h by 2 pi is a constant. So angular momentum resides for a particular orbit. See here n. If it is n equals to 1, if it is n equals to 1, then its angular momentum would be something. If it is n equals to 2, then its angular momentum would be something. So that's why he told that only those orbits are permitted for which the angular momentum of an electron is a whole number multiple of h by 2 and is given by MBR equals to nh by 2 pi, where n should be an integer. 1, 2, 3, n should be an integer. H is a Planck constant and V represents the velocity of electron, mass m is the mass of electron, and r is the radius of the orbit. See, if you finding out n equals to 1, for n equals to 1, then it would be radius. If you finding out n equals to 2, then this would be the radius of the orbit. And radius of the orbit is given by this formula, n square h square by 4 pi square m e square z. N square h square by 4 pi square m e square z. This is the radius of nth orbit. And velocity can be found out by this relation, which is 2 pi e square by nh. Now see, as we have already discussed in the previous section, that if energy has to move from its lower energy state to higher energy state, it will absorb some energy, or of particular frequency or particular wavelength of light, and that energy absorbed is given by energy of where it is going minus energy from where it has gone. So energy absorbed is difference of energy levels, that means E2 minus E1 would be energy required to move it from E1 to E2. When it is in excited state, when it is gone to its excited state, that is E2 state, and we know that in the higher orbit energy is more. If energy is more, that means the electron is less stable. So for stability, it will return to its original position or stationary state. Ground state, it is known as this. E1 is the ground state of electron. So when it moves back to its original position, it will radiate some energy of particular frequency or particular wavelength, and that energy emitted is given by E2 minus E1. Now see, we are moving forward to its next point, which is its ground state or energy state, the ground state. Since energy cannot be lost continuously, here the energy absorbed and here the energy released are all known as quantum of energy, quanta of energy. All the energy absorbed and energy released are one quanta, that these are known as one packet. One packet of energy, two packet of energy is absorbed, or one packet of energy or two packet of energy is released. Okay, so these are quanta. Since energy cannot be lost continuously, an electron continues to move in a particular energy level without losing energy. Such a state of atom is known as its ground state. Such a state of atom where it do not lose energy continuously, it lose energy in the form of packets, or it absorbs energy in the form of packets or quanta. Those one packet is known as quanta, and from where the energy excited, after absorbing energy, it will go to its excited state. The state where it gone to after absorbing energy is known as its excited state. So it's all about ground state and excited state. If we can move forward to its achievement, the first achievement the Bohr described is, or we can find out from Bohr's postulates, is that stability of atom. The first achievement is stability of atom. The first achievement is stability of atom. According to Bohr, electron does not lose energy as long as it revolves in a particular orbit. When electron revolve in a particular orbit, it does not lose energy. The electron lose energy or absorbs energy when it goes from lower energy state to higher energy state, or it comes from higher energy state to lower energy state. Only then electron lose energy, otherwise electron don't lose energy. So that's why, what does it mean? That does mean that the atom is stable. Also, it cannot jump from first orbit to the lower orbit. If the electron in first orbit, then it cannot move backward to its original lower energy state, because there is no orbit after n equals to 1, right? That is known as quantization of the orbit. Thus, gradual loss of energy by the electron is not possible. Hence, atom is stable. Thus, it removes the limitation of Rutherford's model of atom. Number 2 achievement is interpretation of the line spectrum of hydrogen. So, if we can move forward to the interpretation, that is its second achievement, that it interprets the hydrogen spectrum very conveniently. See, we have learned that if the electron jumps from lower energy state to higher energy state, or it comes from higher energy state to lower energy state, it absorbs energy or it's radiate energy, release energy. So, energy difference is E2 minus E1, always E2 minus E1. So, E2 minus E1, E equals to h nu from Einstein energy, E equals to h nu. So, we can find out the frequency of electron, or frequency of that particular electron, the electron which is going from lower energy state to higher energy state, or which is coming from higher energy state to lower energy state. By this, if you put the energy difference, of the orbits, and if you put the value of h, which is Planck constant here, you will get particular wavelength of light, the wavelength of light which is absorbing or which is releasing. See, if you put n equals to 2, and if you put h, value of h, and the energy difference between, let us say, 2 and 3, then you will get the wavelength the light will absorb, or the wavelength the light will release from going from 2 to 3 or 3 to 2. You are getting frequency, and from P equals to C equals to nu lambda, you can find out the wavelength of light also. See, so by this we can see that every orbit has its own energy levels. So, let us say this is the first orbit, second orbit, third orbit, fourth orbit. This is the quantum number or orbit. So, if the electron is in first orbit, if the electron comes from 2, 3, 4, 5, 6, 7, 8, 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1, 7 to 1, 8 to 1, then the series we got, the lines of spectrum we got here is known as Lyman series, and that Lyman series consists in ultraviolet region. If we talk about Balmer series, see Balmer series, that means it is in the second orbit. If it is in the second orbit, then the electron can comes from n equals to 3, n equals to 4, n equals to 5, n equals to 6, and similarly from 7 and from 8. So, we will get a separate region. That separate region is known as your visible region. So, Balmer series is your visible region, it lies in the visible region. And moving forward with the same logic, if we talk about Paschen series, then the electron will comes from n equals to 4, n equals to 5, 6, 7, 8, that is the same logic. We will get separate spectrum series, and that spectrum series, all these series, right, we know these are, this is UV, this is visible, this is infrared, region. P-Fund, bracket, Paschen are infrared region. So, these are the achievements of Bohr postulates which modified the Rutherford atomic model. I am quickly revising the topics we have learned. See, modified Bohr model, actually the modification of Rutherford model, because we know that Rutherford has various limitations of his postulates. The first is stationary states where it lies in a particular state. Energy levels, every orbit has its own energy. The general energy is this. If you put z equals to 1 for hydrogen, you will get the energy of electron, and if you put all the value, you will get energy this. And the third postulate is that the angular momentum is a constant term. The angular momentum is a constant term, and for every orbit, angular momentum is, so see, for every angular for every state it has some specific angular momentum. That means if the electron lies in n equals to 1, it has different angular momentum. If the electron lies in n equals to 2 orbit, then it has particular angular momentum. That angular momentum should be a multiple of nh by 2 pi. That h by 2 pi, we can say this as a new constant because it vigorously used in quantum physics. H by 2 pi is known as h cut. This is h cut. We can write it as h by 2 pi as h cut. So m here we can write it as h cut into n. H cut into n. That means every particular orbit has its own angular momentum, and radius and velocity of particular orbit we can find out by these relations. And second thing is packets or quanta. See, energy cannot lose. Bohr specified that energy cannot lose continuously. Energy cannot lose continuously. We can see or we can verify from hydrogen spectrum, right? From hydrogen spectrum, here we can see that every orbit has its own quanta of energy or own energy levels or spectrum. We are getting this discrete spectrum. We are getting this discrete spectrum because when energy moves from its lower energy state to higher energy state, or it comes from or it back from higher energy state to lower energy state, it absorbs energy or it releases energy in the form of packets. That means in the form of particular energy. That particular energy we can find out by this energy difference of the orbits, which is h nu, and you can find out the frequency. After that you can find out the wavelength also by this relation. When the electron is in a particular orbit, it is in its ground state, and when it moves from that ground state to higher orbit, that energy level is known as its excited state. So we can see that Bohr actually the achievement of Bohr is actually for mainly two things. That is the stability of atom. He completely described the stability of atom, that it cannot have infinite energy. It has, for a particular orbit, it has specific energy at a particular level. And second thing, he certainly described the interpretation, the spectrum of hydrogen by his quantum theory. So that's all about Bohr's model of atom. Let us solve some problem related to the last slide. We have learned the nth orbit, radius of nth orbit, energy of nth orbit, and the velocity of nth orbit related problems. See, the first question is the ionization energy of helium plus. Helium plus means this is hydrogen like atom, right? Because hydrogen has one proton. So if you see this, that helium plus has also one electron, because one electron has gone away. The ionization energy. What is ionization energy? Ionization energy means the energy it requires to for an electron to go away from a particular orbit, or to remove an electron from a particular orbit. The energy required to remove an electron from a particular orbit is known as its ionization energy. Now see, from helium to, we have converted helium plus. That means we have removed one electron by providing some energy. That energy is given as 19.6 into 10 to the minus 18 joule per atom. The question is, calculate the energy of the first stationary state of lithium 2 plus. So it's a very important question. because we know all the information about hydrogen, information is given regarding helium plus, and we have to find out the information about lithium 2 plus. So if you consider this lithium 2 plus, if you see this, that lithium 2 plus is also hydrogen like atom, because the 2 electrons, we have removed 2 electrons from lithium, so now it has 1 electron, or it's a hydrogen like atom. Now see, energy it required, that means the energy of ionization potential, that energy should be same, and energy we know it's negative. So energy to remove 1 electron from helium plus, that is equivalent to minus of ionization potential of helium plus, and it is given as 19.6 into 10 to the minus 18 joule per atom. So energy of helium plus ion we know minus 19.6 into 10 to the minus 18 joule per atom. Now see, all the formula we have learned for hydrogen only. If it is hydrogen like structure, that is helium plus and lithium 2 plus, what you have to do, all the formula by multiply by atomic number square, Z square. So if you are finding out energy of helium plus ion, energy of helium plus ion, then that formula would be atomic number of helium square multiplied by energy of hydrogen. It's very simple, not that difficult. So atomic number of helium is 2, so 2 square is 4. So 4 into energy of hydrogen atom. So what would be the energy of lithium? Same formula, Z square of lithium multiplied by energy of hydrogen atom. Lithium, atomic number of lithium is 3, so 3 square 9, 9 into EH. Divide these two, that is E lithium by E helium, you will get 9EH by 4EH. You have to find out the lithium, energy of lithium, first energy of first stationary state of lithium 2 plus. So lithium 2 plus would be, consider this helium, energy of helium in that side, so E plus He into 9 by 4. We know E plus He, as this. Put the values and you will get the answer. Now our next question is, according to Bohr theory, the electronic energy of hydrogen atom in the nth orbit, nth Bohr orbit is given by this. This relation is provided. Calculate the lowest wavelength of the light that will be needed to remove an electron from the third orbit of helium plus ion. See, the question is given that electron remains in third orbit and you have to remove an electron from third orbit, and that lowest wavelength you have to require, the lowest wavelength of light you have to require, you have to provide. So third orbit, see, there is no information given about from third orbit to which orbit. So that means you have to consider that you are removing that electron completely. That means you are removing that electron from third orbit to infinite, because no information is given. See, for hydrogen atom, energy is given in the question, something like this. But for all other hydrogen like structure atom, it would be only multiply atomic number square, Z square by N square. All these things would be same, but for any other atom or hydrogen like particles, you have to multiply Z square only. So for helium, Z is 2, so 2 square, you got the energy in the third energy level, E3, that means N square is 3 square, N square is 3 square, and atomic number of helium is 2 square. Put the values, you will get the third energy in the third level of helium plus ion. Now energy required to remove an electron from third orbit. From third orbit to where? From third orbit to infinity. So we know E2 minus E1. So here it would be E infinity minus E3. And always remember, energy in infinity is always 0. Energy at infinity is always 0. So E infinity is 0. So delta E would be minus E3. Now minus E3, we know E3. Put the values, minus, and this minus would be plus of this thing. Calculate, you will get the energy. Now see, we know E equals to h nu, or we can say, we can here say that E2 minus E1 is actually H nu, the same thing. So delta E equals to H nu, we know this formula, and nu equals to C by lambda. So H C by lambda. This energy we have calculated now, 9.67 into 10 to the minus 19 joule, and you have to find out the wavelength. Wavelength it required. Let's see the question. Find out the light that will be needed to remove a electron from the third orbit of the ion. Calculate the lowest wavelength. We have to calculate the wavelength. So what would be the wavelength? Cross multiply, wavelength would be lambda equals to Hc by 9.67 into 10 to the minus 19 joule. Put the values, you will get the answer in meter. Wavelength, that is length of wave, unit would be in meter. So after some simplification, you will get it at Armstrong. Always calculate wavelength in Armstrong. 1 Armstrong means 10 to the power minus 10 meter. Now our third question is, suggest two transitions in the atomic spectrum of hydrogen for which wave number ratio is 108:7. This is another type of important sum. It's a manual method. You have to calculate energy or wavelength or wave number in each energy state. See, the normal formula we know, Rydberg equation. This is Rydberg equation. Nu bar, that means wave number is equals to RH 1 by n1 square minus 1 by n2 square. Rydberg constant we know 109628, that something constant term. So in the first line of Lehman series we know, in the Lehman series n1 is lower energy state is n1, n1 is 1 and n2 is 2. You will get first line of energy spectrum. So nu bar would be n1 is 1, n2 is 2. Calculate, you will get 3 by 4r. In the first line of Balmer series, you will get, in the Balmer series we know lower energy state is 2 and higher energy state is 3, because in the first line put the values, you will get something like this. In the first line of Paschen series, n1 is 3, n2 is 4. So you put the values, you will get something like this. Now you need 108:7. So you have to find out the ratio of this Balmer, Paschen, P fund, etc. if you can find out, and you have to find this out, find out the ratio, different combination of ratios. So first we have taken this ratio 1 and 3, that means the Lehman series and Paschen series. So find out the ratio. 3 by 4r is to 7 by 144r. R cancel out, this cancel out. After cancellation you will get 3 is to 7 by 36. So after multiplication and LCM you will get 108:7. So we can see that we got the answer as 108:7. So the transition is, what is the transition? What is the transition? Transition is from Lehman series, that means n1 equals to 1 to Paschen series, that is 3. The transition is from Lehman series to Paschen series. Okay, that's all about the 3 power laws. So see, we have seen that Bohr has many success in its model, but it has also some drawbacks in its model also. The first drawback is it fails to explain the spectrum of multi-electron atom. See, Bohr atomic model is applicable, or Bohr atomic model can be explained the spectrum of hydrogen and hydrogen-like structure, that is hydrogen, helium plus, lithium 2 plus, this type of structure. Hydrogen and hydrogen-like structure. But for multi-electron atom, the spectrum cannot be explained with Bohr atomic model. Now second drawback is, according to Bohr, the circular orbits of the electrons are planar. However, this is not true, and electrons move around in the nucleus in the 3-dimensional space. Electron moves in the 3-dimensional space. We will see in the next slide that electron, actually we have divisions in the orbitals sp, df, all of them are 3D dimensions. Now see, next drawback is it fails to explain the cause of chemical combination and spaces of the molecules arising out of it. So chemical combination, how it combines with other atoms or molecules, it doesn't explain that. number 4 is one of the major drawback of Bohr that it assumes a definite knowledge about position and momentum, that it assumes that you can find out the position and momentum of electron, but according to Heisenberg, you cannot find out the exact location of electron or exact location of electron and the momentum of electron at a particular time. So in that perspective, in the Heisenberg perspective, the Bohr actually fails to explain that. Now number 5 is it cannot explain the relative intensities of spectral lines. So how much it is white, it doesn't explain that. Bohr's theory failed to account for the splitting of spectral lines on the application on the application of magnetic field. See, if you apply magnetic field on the lights coming towards the prism, the lines, the spectral lines will further divided into different lines. That effect is known as Zeeman effect, but Bohr actually failed to explain that. Next, it could not explain the splitting of spectral lines on the application of electric field. If you apply the electric field, if you apply the light on electric field, the spectral lines will again divide into different lines. That effect is known as Stark effect, because he found it out, but he also could not, Bohr also could not find this effect. It fails to explain the fine structure of spectral lines, fine structure, why this is coming, why these fine structures are coming, it doesn't explain that. So all these are drawbacks of Bohr atomic model, though it has a lot of shortcomings or drawbacks, but Bohr is actually successful in explaining the atomic structure in a manner. So let us move forward to our next topic, which is quantum mechanical model of atom. See, in the recent development, until now we have satisfied with the Bohr's theory of atomic model, and after that Sommerfeld has came into the picture, and he explains that hydrogen and hydrogen-like structures or electron, the radiations emitted by the electrons are very satisfactory in the determining of hydrogen spectrum. But in the recent development, we can see that wave nature of material and Heisenberg uncertainty principle has twisted the whole thing in a manner that all particle in motion possess wave character. That means every particle, whether it's a human being, it's a tree, or it's a electron, every one which is in a motion possesses wave character, wave character. In the scenario, de Broglie has came and given its equation. He told that the wavelength of that particle which is in motion, that wavelength is given by lambda equals to h by mv. So let us do a problem related to de Broglie equation. Calculate the kinetic energy of an alpha particle which has a wavelength of 12 picometer. Mass of alpha particle is given, we know lambda equals to h by mv. So lambda is given as 12 picometer, that means 12 into 10 to the power minus 12 meter. We know h, Planck constant, we know mass. Put the values, calculate velocity, and unit kinetic energy, which is half mv square. Put the value of v square and the mass of electron. You will get the kinetic energy of the alpha particle. Next, see Heisenberg uncertainty principle. It is very important because see Heisenberg told that the position of an electron and the momentum is mass into velocity. As mass is constant, so velocity can be changed. So delta x multiplied by delta p is greater than equals to h by 4 pi, That means Heisenberg told that the position and momentum of electron in a particular orbit at a particular time cannot be you cannot tell the momentum and position very clearly, because see, if that electron which is revolving in a orbit, if that electron got a photon E equals to h nu, if that electron got a photon of energy equals to h nu, only one photon of energy, still the electron will change its momentum because it got some energy, right? If it got some energy, then it will change its position immediately. So you cannot say the position which it is lying, where it is lying, and the momentum of that electron at the same time, That's all about Heisenberg uncertainty principle. In other words, you can say that you cannot measure where the electron is lying and what is the velocity of electron. You can measure either the position of electron, you can measure either the velocity of electron at a particular time at a particular position, but you cannot measure both of them, where it is lying and what is the velocity at that time. You cannot measure the both, and it is his formula. And by this, see, if we extend our knowledge in the Bohr's theory of atomic model, in Bohr's told that electron is revolving in a particular orbit, right? If it is moving in a particular orbit, then it has some angular momentum and velocity, and it has some position also. But when Heisenberg told that you cannot explain, or you cannot find out the exact position and exact velocity of electron in a particular moment or particular position, then the whole scenario changes. That's why the term came quantum mechanical model, and from this we can say that the radiations emitted by hydrogen, actually has two properties. One is particle nature, and number two is wave nature. That two property we can say from wave nature, that is the de Broglie, from de Broglie wave equation we can find out the lambda, because if any particle has velocity, then it should have some wavelength associated with it. But when it came to large objects, then lambda is immaterial. So Heisenberg uncertainty principle is immaterial for large objects. But when we consider the small electrons or small particles, then Heisenberg uncertainty principle is applicable, and it is very useful in quantum mechanical model of atom. In the next scenario, we will learn about wave mechanical model of atom. We will do in the next class. We are running out of time. All the best today. Thank you.